Our first speaker is Adam Warmoth. He is the Vehicle Requirements Lead at Uber Elevate, where he focuses on system-level technical and economic analysis. Adam joined Uber after graduating from Stanford with a BS in engineering physics and an MS in mechanical engineering. While at Stanford, he worked on electric flight through a research position in Dr. Ilan Kroo's aircraft design group and an internship at Kitty Hawk. His presentation is Path to Scale for Aerial Ride-Sharing. Please welcome Adam.
Thank you to Cafe for having me. This is my first Oshkosh and hopefully first of many, so very happy to be here. And happy to share with you kind of Uber's vision for air ride sharing. And so Peter did a nice job teeing me up with the history that got us to this point, where we have cars kind of all over the cities and creating massive congestion and emission problems. As he said, 50% of the world's population today lives in cities. The UN estimates within 10 years that 6 billion people will live in the world's cities. And so this congestion problem and emissions problem is only going to get worse. And so, Uber's tried different ways to solve this. So as he said, the bike sharing, integrating multimodal options into the app, partnering with transit agencies, Uber Pool, Express Pool. But there's a limit to kind of how much we can do with this limited ground infrastructure. And so we're going to have to take something out of the page of the book of cities and use the third dimension to really unlock the full capabilities of our transportation network. And so, people have been promised flying cars, for 40 years since, in popular science, you saw, okay, in 2 years, everyone will have their own flying car, and so there's kind of a confluence of things that's coming together to make it that it's now actually very close to reality. And so how is Uber looking at solving this problem? And so we've taken massive amounts of data that we have from both our rideshare network and other sources through government and other partnerships to look at how people move around cities today. And you could argue that, with the combination of these data sources, we have, the most complex view of how people move in cities and what choices they make every day, and understanding not just volumes, but inflows and outflows, as you can see with the colors, and really understand not just volumes of flow, but directions and seasonality and all of those kind of complexities that come with estimating demand. And so this is a view of Los Angeles. You can see kind of key landmarks of downtown and LAX and see how people's needs for transportation change throughout the day. And so I know Carl had a question or took a question about, how do you model what choices will people make? And so we've set up these stated preference surveys where we offer these options to people. And and say, given these options that you have today, and given this option that you would have in the future, what kind of mode would you choose? And use that to, ingest all that data into a complex demand choice model to actually figure out, okay, how will people use this service, and how will they kind of react to this new option? And so from this kind of network data and understanding how people flow through cities comes the vehicle requirements. Traditionally, sometimes in aerospace, there's been a tendency to design the plane and then kind of figure out what the network and what the market looks like. And so we're taking very much a market-first approach and seeing how does the different vehicle designs impact if we're able to actually serve people and if we're able to actually scale this service. And so what you saw in this picture is that at 100 miles an hour, if we want to deliver the time savings that's required to get people to actually use this service and pay for the service, you have a pretty limited radius from which you can pull riders and still save them time with all these kind of multimodal switching costs. And so by going from 100 to 150 miles an hour, you would think you would start getting some decreased marginal returns because of that switching cost. But actually, it's kind of the opposite, is that the radius you can then pull from now doubles, and now the area you can pull from quadruples. And pulling in those people is really what's going to be key to making this work in a ride-sharing model, and kind of why it hasn't worked in the personal ownership model in the past. And so being able to effectively pool these riders, batch these riders with a multimodal network is kind of driving how we define the vehicle requirements. And so we've done kind of complex analysis on kind of each part of a vehicle design, looking at payload, looking at passenger weight distributions, looking at expected load factors. Again, with speed, looking at how that impacts our multimodal network and how much people will pay for those time savings. And so we've done analysis kind of across the value chain. Again, with the infrastructure, part of a major reason pushing us towards the all-electric solution compared to a hybrid is that the fire safety regulations, when you have liquid fuel on board, are much more stringent. You have to have a foam safety suppression system, which adds cost. You have to have filters. A lot of these are going to be on rooftops where the air intakes for buildings are. So there's a lot of kind of complexities that you have to take into account. Not just like, hey, hybrid gives me more range, but how are we going to fuel these? And not even just the fueling, because you don't need to fuel as often, but the fire safety really is going to be a major impact on being able to scale this network efficiently. And so kind of what has come out of this analysis and kind of requirements deep dive is a set of kind of vehicle requirements that we've released a short version publicly on our website that you can view. We have a deeper kind of requirements document that has all the substantiation behind it for our partners. But the kind of mission that comes out of this that hasn't been used in traditional aerospace is this 3-hour sawtooth kind of rush hour pattern. And so this is sizing, how do we design our battery to be able to withstand these charge rates? And then looking at the network level and saying, okay, how long can we charge for before we start taking hits on throughput? How long can you charge for before you're not getting enough throughput to compensate the infrastructure owner accordingly to where it becomes infeasible? So we've really taken kind of this whole system level approach to understanding what the vehicle requirements are going to be and also understanding what the technology can do. So again, we can't design the vehicles in a vacuum, and we also can't design the network in a vacuum. We can't design a network that has vehicles that fly 250 miles an hour for 500 miles range, because the vehicles can't do that. But we also can't design just the vehicle in a vacuum and not understand the impacts it'll have on the network. So a kind of a simple trade study, kind of an example of a simple trade study here would be, okay, to hit the range that you need to kind of serve a whole metropolitan area, there's kind of a minimum battery size that you need. This is for like a generic lift plus cruise configuration. But then you have to kind of take the operational constraints into account. And we're saying that the kind of average mission is going to be closer to 25 miles, and that's the mission that you're going to need to do repeatedly with kind of minimum time on ground. And so then you want to be able to do that for kind of the 3-hour rush hour so that you can maximize your throughput in that max peak demand hours, and then you can do the longer charges during the off-peak hours. So this kind of creates this design space, and obviously there's a lot more variables, a lot more constraints to consider, but this kind of gives you an example of how the network and the vehicle have to be designed in tandem. And so we've all seen this VTOL wheel. Todd called it on the first day the wheel of misfortune. And so my colleague Ian Villa, in collaboration with Mike Hirschberg from the Vertical Flight Society, have worked on the new VTOL wheel, which will hopefully be a more fortunate version. And so we have concepts from around the ecosystem here. And obviously I think there's now more than 100 concepts on eVTOL.news. So this isn't fully comprehensive, but kind of gives an overview of the different approaches that people are taking to solve these problems and to create an urban air mobility network. And so at Uber, we never intend to design or build a vehicle, but we realize that there's this need to have this ecosystem, this very collaborative approach up front, but also understanding that our vehicle partners need to have their own, protect their technology, protect their IP. And so we've released this series of eVTOL common reference models with the intention of allowing government and academia to engage. We're working on tool development, attacking those issues of noise, attacking those issues of transition that traditional tool sets don't address, and having a kind of common model, taking a page out of NASA's book with their high-lift common reference model, or common research model. And then also kind of exploring some technologies here, like our stacked co-rotating propellers, which we're studying with the collaboration with LaunchPoint and with the Army Research Laboratory to understand how you can use this old technology of stacked propellers, but with a twist of separate electric motors, change the azimuth angle to create higher CLs, better figure of merit and static hover, lower noise. And so this is we're not saying that this is the solution, but here's a way that you could integrate this technology. Here's a vehicle that kind of starts to show what kind of vehicle can meet the requirements that you need for an urban air mobility network. And so we've kind of iterated on this. Again, we're not saying that this is the one answer, so we're developing more common reference models. This is a fully separated lift plus cruise versus the tilt rotors on the first one. And then, there we go. Oh, sorry. This is a video, I think. Okay. So this is the third common reference model. We're going to have a 5-foot model that's on display at the Gamma booth this week, so come by and see it. And again, it's just showing another way to kind of integrate these technologies and show that this is a really wide design space and allow people to kind of collaborate on how do we analyze these new types of vehicles. And so we're really excited to have 5 amazing partners in this journey with us on the vehicle side. We've got Ed here representing Aurora, and we've got other great partners. Again, Pipistrel with a great tradition in electric flight with the Green Flight Challenge. And so we're really excited to have this expertise in these OEMs that are providing their knowledge and their experience to this ecosystem as we provide ours on the network modeling side and the multimodal piece. And so that's kind of the whole approach we're taking, is this ecosystem approach where we're working with a lot of partners. We're partnering with a cell company called Molicell, and so we did a test trade study with Carum to see would their concept be able to fly and meet this mission even with today's batteries, and showing how the cell voltage handles kind of these low state of charge at the end of that 3-hour sprint, which in a network where you want to be optimizing and minimizing your time on ground, a lot of time is going to be in that range. So how does that affect the power draw of the cells? And their concept was able to theoretically get through the 3-hour sprint even with today's cells. So that was a great kind of proof of concept that the requirements that we're designing towards are a feasible kind of solution in this space. And so we're envisioning the cost. We've talked a lot about the cost today, and George shared a lot about the electric technology that drives us down the cost curve. So the kind of first thing that gets us down to kind of Uber Black-like cost per mile prices is just that switch from the traditional fuel-burning, complex mechanical systems to motors with single just bearings as moving parts, and this distributed electric propulsion and the design freedom that unlocks. And then when you add in the ride-sharing piece, and you're able to up your utilization and your load factor at the same time, so you're able to do these on-demand flights, but also fill every seat, which you can't really do without kind of a ride-sharing model and a multimodal network. That really gets you down to that kind of UberX-like price, at which point you can really start scaling. And then long-term, as we figure out how to develop composites, and once we have autonomous systems that are flying these, the costs drop down even lower to the point where it becomes irrational to drive your own car. And so this is kind of one part of Uber's vision to kind of create a better version of urban mobility that doesn't rely on personal cars, personal single occupant fuel-burning cars. And so kind of with this understanding of the pricing model, with the understanding of demand, with the understanding of the vehicle's capabilities, we look at, okay, what will this network look like at scale? And what are we going to need to do to be able to actually meet this demand, right? We can say that there's all this demand there, but we need to actually meet it. And so we've developed Skyport Concepts. This would be one that could just be retrofitted onto an existing parking garage. And so this is something that could be stood up quickly. The first version of this could just be a shipping container and a couple painted lines on the top of the parking garage there. And then as the network scales, the infrastructure can scale along with it. But we saw in some of these mega cities like LA, there was even more demand than possibly these types of infrastructure could serve. And so we worked with 5 different architectural firms to design kind of what the Skyports of the future would look like. And you can see this one's built over a freeway, so it's integrating with existing transportation options and creating this kind of modular, scalable design that can really support the scale in the future. Also, there's the air traffic constraints. So that's something we've identified, and we're working with NASA. We have a Space Act agreement with NASA to work through these air traffic management problems. And our director of airspace, Tom Prevost, has kind of come up with this dynamic Skylane network concept where you're projecting out kind of your 4D trajectory, and you have these lanes that are changing as the wind patterns change, as other traffic changes, and is able to serve not only our needs, but also the needs of the other players in this ecosystem. And there's also an incredible amount of complexity. I'll just keep clicking back to this. In terms of operations, and this is what really needs to all be brought together in order to make this all work. And so there's a bunch of roles that all need to be played, and that's where this ecosystem, I'll just leave it for now. This ecosystem is really important in terms of everyone kind of playing their role within this ecosystem, and then kind of needs an integrator to bring it all together and be managing, and understanding the stated charge of the batteries and, where the demand is and where the projected demand is and where, the storms may be, and integrating all of this information to make safe decisions and to make economically optimal decisions. And so we have a lot of partners in this effort, and we'd love to have more. So if you're interested in working with us, you can contact us at elevate@uber.com, and thanks.